Hey everyone, welcome to this video, understanding IPv6 and then understanding, well, how does Azure work with IPv6? As always, if this is useful, please go ahead and like, subscribe, comment and share and hit that bell icon to get notified of new content. Now, my original goal for this video was just to talk about IPv6 in Azure. Then I quickly realized to really make sense of that, it was an important thing to understand IPv6 and some of the differences in how that actually functions and some of the intent. So really this video is in two parts. If you just care about IPv6 and not Azure, you can just watch the first part. If you only care about the Azure implication, watch the second part. If you're kind of interested in all of it, there you go, watch all of it. Now, when we think about IP, before we start talking about Internet Protocol, let's just talk a little bit about some of the actual physical structure. So I can think about there are links. I have a link, a network segment, or a subnet, a local link, on which machines that are connected can talk directly to each other. Now I'm drawing these as PCs. In this case, they could be servers, they could be IoT sensors, they could be microwaves. The point is they're on some local network segment. Often they'll be maybe connected to a layer 2 switch. Now this particular network segment, well, there's going to be multiple network segments. There might be another network segment over here with its kind of group of machines. And one of the key points of these network segments is machines on the same local network segment or subnet can directly talk to each other. If I want to talk to someone on a different network segment, what then happens is we have routers. So these are these kind of layer 3 and above devices that would enable me to communicate to other parts of the network. And often what will actually happen is, so we have a whole hierarchy of these routers. So there might be other routers connecting to other network kind of segments over here. They might roll up to some kind of router aggregation points. And then ultimately what happens is if you think about what is the internet, well, the internet is not any magical thing. If we think about, well, really, what is the internet? The internet is just a whole bunch of networks connected together that exchange routing information. So the internet is, hey, all the networks connect together and they exchange routing information. So that's really all the internet is. But it obviously to exchange that routing information and to send the packets over the wire, it needs a common protocol that everyone agrees to and understands. And I need to make sure, well, addresses don't clash with each other, just like in the real world. I need unique street addresses so I can send communications to different places. And this is where the Internet Protocol comes in, i.e. IP. So we often think about the OSI model, where we have these various different layers. And I can really think about, well, at layer 3, that's where we have the Internet Protocol. And there's two versions of this. We have the v4 and then the v6. Now on top of this, at things like layer 4, you have things like TCP, UDP, for example. Then there's other layers that go on top of that. Underneath this, we have the data link layer, which has the physical MAC addresses of the equipment. Then the actual physical layer that gets the bits over the wire. And I actually want to start by reviewing the IPv4 because I think it's important to understand how that works and the types of addressing we actually see with IPv4 and how that really exists in this physical network. So if I think about IPv4, and let's give that orange, we think IPv4. And we're probably all used to this idea that it's a 32-bit address. i.e., there are 32 ones or zeros that actually make up the address. And so we often see this as 4 numbers from 0 to 255. Each number represents 8 bits. So if for an example of this, I could think about, well, okay, 0001010. And we can just kind of keep extrapolating that out. I'm going to be lazy, 000000001. And then we keep kind of scrolling over. I could be a 000000010, and then some other number, 0000010. And each segment of this, remember, this is 8 bits. And if you think about the way we actually translate that to a decimal number, well, that's a value of 1, 2, 4, 8, 16, 32, 64, 128. That lines up with the bits going this way, which means each segment of this has a value between 0 and 255. So if I was to really look at this address right here, well, so that's the 2 and the 4, sorry, the 2 and the 8. So that's 10.1.2.4. So that's how I could really think about that IPv4 address. So all we're doing is taking that 32 bits, we break it up into 4 groups so it's a bit easier for us to understand, and then we create this decimal number. So 10.1.2.4. We're used to seeing IP addresses in that way. Now, if we talked about this idea of the physical network and having those different segments or subnets, I need to understand if I'm a machine, well, what machines can I talk to directly, i.e. I'm the same local link, and which are on another part, I would have to send it to a router. I have a default gateway, which is my default place to send it to, or I might have specific routes and send it to different places for different parts of the network. So what we need to be able to do is to take that address, so let's kind of dive into this for a second. So this 10.1.2.4. I have to be able to work out which part is the network and which part is the actual host. Now, what we're used to seeing in an IPv4 world is we see a subnet mask. And we'd see a subnet mask like, hey, 255.255.255.0, which is a binary operation to tell us which bit is the network and which bit is the host address, which is super simple to see from that. Okay, well, all of those blocks, 255, so that segment is the network, and that part is the host. So if I was talking to anything that was 10.1.2. something, hey, I can talk to it directly. If not, hey, I know I need to go via my default gateway, or maybe I've got a more specific route. Now, another way of writing that, remember, each one of these is 8 bits. So 8, 16, 24 bits. There's a CIDR format, classless interdomain routing. So I could also write /24. So that's telling me the first 24 bits are the network address. So it's a way to really divide that up. And that means the same thing. I'm going across that way. Now with that IPv4, we do actually see different types of address. Now one of those common ones we're going to see is if I think of any particular device. So let's say look at this device right here. Well, I might see 127.0.0.1. That's the loopback address, i.e. that's me. So what about when we actually want to start talking to other things? Well, if we remember, in this example, this wire, this is a particular subnet. We'll say it's a particular segment of the network, but we'll say this is kind of subnet 1 for an example here. So that's a certain link, a segment of the network. When I think of IPv4, sometimes what we'll actually see is this 169.254 address. And that's generally a bad day. So what we have is this ability to say, okay, I could have a scope of just my local link. It won't work anything beyond that, but we have this APIPA. So that's all about automatic private IP addressing. And that's going to be something 169.254.0.0/16. i.e., what I actually get out is going to start with 169.254, but then these parts really could be anything. So the point of this automatic addressing is if I'm a client on a network and I don't have a manually configured IP address, and there's no service that gives me out an IP address. Normally we shout out over the network a boot P request, hey, I need an IP, and a nice DHCP server, Dynamic Host Configuration Protocol, will say, oh, hey, here's an IP address from a port I have. But no one's answering. So we can have this option that, hey, if nothing is available, we have this address that I can use to talk to anything on the same local link network. But I can't talk to anything beyond. The routers will ignore it. They're not going to do anything with that traffic. So that's the scope of what I can do with that. The next thing we kind of see, if I think about my entire network, is we have this idea of RFC 1918. So RFC 1918 you are probably looking at this right now. If you go and look at what is your IP address, chances are you have an RFC 1918. So this has kind of a 10/8. There's a 172.16/12 and a 192.168/16. So there's a different group of IPs available. The point of RFC 1918, as we're going to see, is they ran out of IPv4 addresses. And so the problem was, well, what do we do? The solution was these group of IPs were reserved. And they were reserved for using on our internal networks. We could use it across our entire corporate network, across multiple locations, different geographies. And the routers would route this internally on our network. So this RFC 19 right here also works all the way up to kind of that edge router here. So I can use that same RFC 1918 there. So everyone in my network can get an IP address from here, route all to the different networks, but it will not route out to the internet. And the whole point of this was designed around the fact that, hey, we've run out of IPv4 addresses. So internally in our network, this AEP-IPA is no good because I can't talk to things on other network segments. So we had this RFC 1918 that would work. Our internal routers will route this, but the internet will not. Internet routers and your edge router would drop this stuff. And what actually happens is your edge routers that talk to the internet do something called network address translation. They do have an IP address that will route on the internet, and it translates all the requests and it maps it to a certain port so it can keep track of who's asking for what and send the responses to the right backend machine. But that's how that actually functions. So if you go and look at your IP address right now, chances are it's 10 dot something, 172.16.17.18, or 192.168, because you're using that RFC 1918 in your internal network, and then something else is translating that at the gateway to enable me to talk to the internet. Okay, so then how do I talk to the internet? How does that part actually work? So in an IPv4 world, what happens kind of next is, well, we actually get, they're assigned centrally. So there's different bodies for this, but the IANA will actually give out portions of the IP space for IPv4. Now the reality is, you are not going, unless you're a really big company, going to the INA. It's actually probably going to be your kind of ISP. So your ISP has a publicly addressable set of IPv4, and then you go and buy your business class service provider, or even at home, they give you an IP from their selection. So what's going to happen is on your edge device of your corporate network, you have an internet routable IP. This could be, for example, maybe my edge is 203.0.113.5. And that acts on behalf of all of that RFC 19 internal space to enable it to actually go and talk and participate in the internet. And again, the only point of that was there just wasn't enough IP space for every machine internally to have a valid IPv4 address. Now, some companies might, most will not. An important thing to understand about this network address translation that kind of happens here in an IPv4 world, it is not a security mechanism. It's to handle, I don't have a valid IP space, there's not enough addresses. Security is done through firewalls and stateful inspection. NAT by itself is not a security mechanism. It's not NAT that gets us security. I have the firewall rules, I have the packet inspection. That's what actually gets me security. And that's an important point to understand. Some people confuse NAT for security. It's not. There's nothing about NAT that's a security feature. It's to handle the fact there's not enough IPv4 addresses, and that's really it. Now in IPv4, there's also multicast. I can have an address that goes to multiple network interfaces, so one-to-many communications. There's also broadcast. Hey, just send this out to everyone on my local network segment. So that's IPv4. And I just wanted to kind of set the groundwork. It's 32-bit address, which is a lot of addresses, but coffee machines, my wife has got a new coffee machine, it connects to the internet. You have fridges, microwaves, IoT sensors. Everything has an IP address now. And so there's just not enough of them. We ran out. And so things like RFC 1918 and NAT help with that, but there were other challenges around header flexibility, route aggregation, and more. And so we get to this idea that, well, we really need this IPv6. This is the future. And ideally what we want is we don't want to have this same problem a few years down the line where we run out again. So we want to get a nice IP space that this time is going to last. So if the IPv4 was 32 bits, for IPv6, it's 128 bits. That is really, really big. That is 2 to the power of 128. If we bring up the calculator for a second, so let's just go and look at our calculator. If in our calculator we did 2 to the power of 128, that's 3.4 to the power 38. 38 zeros. That's a really, really, really big number. In fact, what I've heard is that number is actually enough to give every atom on the surface of the planet Earth an IP address with enough left over to cover another 100 Earths. i.e., we really shouldn't run out this time. Now, the intention is actually not to use every one of these IP addresses, and we'll see this. It's designed to be so big that we can be very efficient in terms of just allocating blocks of IPs and not having to do some very weird and natural stuff we had to do before with IPv4. We can just have these nice blocks of IP addresses to make it very simple for the network portion and the host portion and the routing of these things and the allocation. It's going to be a lot neater. So we have that massive number of zeros compared to the 4 billion we got with IPv4, which is like, we're not going to run out this time. So the whole point is we want this massive space so that we can really be optimized in our interactions with this. The reality today is if I actually think about a machine, what you're commonly going to hear is the idea of being dual stack. And what dual stack means is I still have IPv4, but I have IPv6 as well. So I have both sets of IP supported. And I'll use whichever one I need for the particular thing we're actually going to use. Now remember, when we talk about IP is layer 3. So when we move from IPv4 to IPv6, or we start using IPv6, this is not, oh, I have to have a second network wire. There is not a separate internet. It's the same wire. There's the same layer 2 with MAC addresses, the same bits of wire that carry the bits over the wire. All that's happening though is the operating systems involved have to understand IPv6, and the routers have to be IPv6 enabled to understand the different IPv6 routes, to maybe help give out the IPv6 addresses, to offer services over IPv6. And IPv6 really is growing. So if we actually look, Google tracks this, which is fairly interesting. So you can go and look on Google, and it's collecting information, and we can see right now that native amount is about 1/3. So we can see right now, about 1/3 of the internet traffic going to Google is IPv6. And it does vary by country. So you can kind of see the United States is actually 46% talking to Google is IPv6. So it really is growing at a pretty big rate. So not a separate wire. It really is just about enabling at the client side and a lot of router configuration to start using IPv6. Now, at home, chances are you're using IPv6 already, and we'll kind of dive into this in a little bit. But it's really just a set of configurations on the router to say, hey, I'm going to start participating in IPv6 and help you work out what your IPv6 address actually should be. Okay, so 128 bits. We do not write it like an IPv4 address. That really is just not practical. If we think about 4 numbers was 32 bits, well now I'm 4 times that. So instead of 4 numbers, I'll be writing 16 numbers. I don't want to, doesn't really work. So with what we actually do with IPv6, we break it down into groups of bits. So we actually break it down into 8 groups of 16 bits. So 8 times 16, we get 128. And each one of those 16-bit groups is called a hextet. So I'm going to break this down into just a particular part of this. So let's just say, okay, we're going to break it down into a particular segment. So I might say, okay, 0, 0, 0, 1, 1, 0, 1, 0, 0, 1, 0, 0, and then 1, 1, 0, 1. So that's 16 bits. And the way we're actually going to write each of the 4 bits is as a hexadecimal character. So each of these could have a value from 0 to F. Hexadecimal, 0 to F. So A, for example, is 10, B is 11, C is 12, B, all the way up to 15. So it can really range from 0 to 15. We use a letter for that. So if I looked at what this value is, well, that's 1. This is a value of 8 plus 2, so 10. So 10 is an A, i.e. 10. 1, 2, 4. And then 8 plus 4 plus 1. So that would be 13. So that's a D. So 1A4D would be my first hextet, and I would have 8 of these. So my entire address will be 8 of those. And we separate the different components with a colon instead of just a dot this time. So we have a whole set of these to actually break it down. So obviously these get very, very, very long. There are some shortening standards we're going to leverage. But before we do that, let's have a quick look actually at a virtual machine. So over here, this is my virtual machine running in Azure, and I've just done an IP config. And what we can actually see is we can see some of these IP addresses. So we have this one here, a link local IPv6 address. And we see it's that FE80, so that's 1 hextet. We see this weird double colon thing, okay? And then we see another hextet, another hextet, another hextet, and another one. So you can kind of see what that address actually looks like. We also see we have a regular IPv6 address up here. This time, it has kind of 4 hex texts in a row. But again, why are there only 3 characters or 1 character, and double colon then another character? So there's obviously something a little bit weird going on with how it's actually presenting those IPv6 addresses. And it's really about optimizing how we want to work with these. Because I don't want to write out, we often are not writing them out. We use things like DNS, so we have nice names. But even then, we want to try and optimize our interactions with this. So let's take a really extreme example. Imagine my binary for just that first hex text was just 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1. So what's the value of that? So my hex text in hex would be 0, 0, 0, 1. Well, there are rules we can actually apply to shorten this. So I'm now going to write out the hex text instead of the actual binary. Okay, so we're going to have 8 groups from those characters. So I can imagine my address might be 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Probably going to miss one at this rate. 1, 2, 3, 4, 5, 6, 7. That's an IPv6 address. I do not want to deal with that, especially if I just want to write 1. And we'll understand why we have that in a second. So there are rules we can apply. So to this address, there's 2 particular things we can use. Firstly, we can remove any leading zeros from each group. Okay, so I can remove those 3 and those 3 and those 3 and those 3. So now I've got 0, colon, 0, colon, 0, colon, 0. What we can also do, in fact, let's just write that out. So now I get 0, 1, 2, 4. Well, that's a lot nicer. The other thing we can do once in each address, we can't do it more than once. Once in each address, any consecutive groups of zeros we can replace with colon, colon. Well, they're all 0, so I can do colon, colon, 1. Now, if my example had instead actually have been, let's say it was 0, colon, 3. 1, 2, 3, 4, 5, 6. If it was that, I could do 0, colon, 3, colon, colon, 1. Because you can only put it in once. The whole point is I can work out what the 0 ones are. Okay, I've got 0, 3, so I know the first 2. And then I've got colon, colon, then I've got 1. Well, that means all the ones in between that must have been all zeros. If I had double colon multiple times, I can't mathematically work out how many consecutive groups there were. So once in your address, you can do colon, colon. It's kind of not super clear right there. So just once, you can do colon, colon. So this gave me that colon, colon, 1. Now, colon, colon, 1, just while we're kind of talking about this, that is the loopback address. So in IPv6 terms, colon, colon, 1 is the same as 127.0.0.1, i.e. there's no place like colon, colon, 1. That is your loopback address. Let's take another example, maybe extrapolate a bit more realistic. So that's kind of giving me the idea of how I can reduce the addresses. So that's why you see weird things. That's why on this VM, remember when we looked at it, for that link local address, what is it telling us? We had this double colon. So it's telling us FE80 colon colon, so a bunch of 0 consecutive groups. And then it gave us 4 hex texts. So if we know we have to have 8 of them, well, we can work out. So it must have been FE80 colon 0 colon 0 colon 0 colon, and then those 4. So that's why we can only have it once. I can work out where that group of zeros actually was. So let's take a bit more realistic of an address, just to really make sure we're understanding the whole point of that. So this time I'm going to do an address, and again it's a big long address, but maybe it's 2001 colon 0DB8, yep, colon 0 ace colon, I think I do the little thing through the zeros. There is no letter O because it only goes up, remember, to F, but there we go. 0, 0, 0, 1. And then, okay, I'm going to have a whole bunch of zeros. So if we follow our rules that we kind of talked about before, remember, what do our rules let us do? Preceding, so leading zeros we can remove. Obviously, we cannot remove trailing zeros. That would change the value. But I can remove leading zeros. And then what? Actually, I did that wrong. Okay, I didn't mean to do zero. I did the binary by mistake. I get confused with binary and just regular numbers. That should have been 0, 0, 0, 4. Problem when you have binary. So I can remove those as well. Okay, so we removed the preceding zeros. And now remember, I can remove consecutive sets of zeros. So those 3 is a consecutive set of 0 right there. So I can change this group to colon, colon, which then gets me a number, remember, of, okay, 2001 DB8 ace colon 1 colon, colon 4. Does that make sense? That's how we're breaking down that number. So we're switching all those out, so we can really clean up the addresses. Now with IPv4, we still have the idea of obviously a network portion and the host address. Who can I talk to directly? Who do I have to go via a router? In IPv4, we would often create these very strange subnet masks and number of bits because we were short on IP space. We had to do very unnatural things to be as optimal as possible. We don't really have that with IPv6 because of the size of the address space. So there's no such thing as a subnet mask. There is no subnet mask in IPv6. We're never going to see a FFFF colon FFFF. We don't do that. We always use the CIDR format. So what that would mean in this case is, well, let's say if I did /64. So I'm saying 64 is where we separate the prefix, the network prefix, from the interface identifier. So in this case, if I looked at this above, so 64 bits, remember, each one of these is 16. 16, 32, 48, 64. So that tells me that is the prefix, because I said it was 64. And that means the interface ID, this is the interface. We don't say host because it doesn't have to be a host. This is the interface identifier. Well, that's going to be 128 minus 64, which is 64 as well. So that's the prefix. In this case, that's the interface ID. So I can quickly tell now, or the computer can quickly tell, hey, which bit is the same network subnet, and which would be different ones if this value was different. So that's really the whole point of this. Now, /64, let's kind of drill on that for a second. Again, IPv4, it was very common because of the shortage of IP space, you would see very strange numbers. It'll be like, hey, you could use a /29 minimum, or maybe use a /27, because we were trying to be as optimal as possible with each subnet because we had a very limited amount of space. This is not the case with IPv6. We're not worried about running out of IP addresses. Again, that's the point of it being 128 bits. It's so big, I don't have to do unnatural and weird things when I think about the number of bits for the prefix. And so in all reality, in terms of the end client configuration, you are nearly always going to see /64. Now, in terms of router configuration, in terms of maybe dividing up address spaces, in terms of routing aggregations, it may do something other than 64. And we're going to dive into a bit of detail about this. But to all intents and purposes, the end client will pretty much always have a prefix of 64 for the network, and the interface ID will be 64 bits as well. 64 is very nice for computers. We have that 32, a multiplier of 32 bits, which is a good computational boundary. It helps with things like mapping to MAC addresses, which are 48 bits today, but there is a spec for 64 bits. It enables us to do things like automatic address assignment. And so, yes, behind the scenes, they may do things other than 64, but your configuration is pretty much always going to be a /64. And so I can really think about that IPv6 address is separated into the network prefix and then the interface ID. And they're going to be 64 bits each in terms of what we actually see. Now, just like with IPv4, but actually a lot more specific, there are different types of addresses, depending on who am I trying to talk to. At minimum, we're going to have a link local address. So if I think about this picture right here, one of the types we're going to see with IPv6 is we have this idea of link local. Now, link local is always going to be FE80 and then some address. Now, the FE80 strictly is just the first 10 bits. Sorry, not bit. Yeah, the /10. So that's 4, 8, and then half the next one. The reality is the specification for link local actually says, yes, while we're only saying the first 10 bits is kind of the FE8 in reality, the rest of it should be zeros. And so it's going to be kind of FE80 is what you're going to see in pretty much all of the time. So we have this FE80 and then an interface identifier. So FE80 is that network segment, and then you're going to have an interface identifier added to it. Now, this is not like this APIPA in terms of, oh, this is ugly, we don't want it. This is actually a core part of how things function. Every device will have one and only one link local address. The router will have a link local. Now, it might be FE80::1. And it can be the same on each kind of segment it connects to. It doesn't have to be ::1. We'll actually see Azure doesn't use ::1. But this is actually a core part. This link local is always used to actually talk to the default gateway within my network. And it's a core part of how things actually function. If I look back at my virtual machine again, remember, we saw we had a link local address. We have that idea of, sure enough, that link local, hey, FE80, and then we see those two colons because the next 3 hextets that can be part of that network are just all zeros. And then we actually have our 64-bit interface identifier, which in this case is basically randomly generated. So that's kind of a core part. Now, the other thing is, remember the default gateway I said? Well, that's FE80 as well. So we can see that's the default gateway for the IPv6, FE80. Now, this is an Azure VM. It does not use 1. It does 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, 10, 11, 12. And then the preceding 1 hextet at the interface, they have set to 0. So that's why there's only 3 characters there, 3 blocks of hextets. So we can see that link local is there. And that link local is actually always there. Even if my network has not been enabled for IPv6, most operating systems are IPv6 enabled by default. So this is another VM I have running in Azure. This virtual network does not have IPv6 enabled. But even though it doesn't, it still has a link local IP address. So it could technically still talk to other machines actually on that same network segment. So there's no actual gateway for IPv6. There's no other types of address for IPv6, but it does have a link local, even though the network it's on does not have IPv6 enabled, because the machine is like, well, I have IPv6 enabled in my protocol stack, well, I can talk IPv6. So it still actually has that link local address. Now, you saw in Azure that link local was a weird, because Azure is software-defined networking. It's not actually real wires or routers with that address. There's a whole SDN stack that captures the packets when they go out. So that's why it actually looks a little bit different. And so when I think of IPv6, let's kind of draw out the IPv6 types of addressing we're going to have. So with IPv6, always, no matter what, we have a link local. I will always have one. So it's always going to be there. And you saw, even if I don't have IPv6 on my network, nearly all modern operating systems are going to create that link local. And the link local is going to be that FE80. Now, again, from a strict protocol perspective, the correct way of saying it would be FE80/10. But the RFC specification for our IPv6, and again, how we as the client see it, mandates that the remaining 54 bits, remember 64 bits in what is typically a network prefix, it's saying the first 10 is that value, that FE80, which means the rest of them, the other 54 bits, could be any value which would change potentially other parts. But in the specification, it says all of the other 50 bits are 0, which means it's always going to be FE80 and then your interface ID. And reality is it's kind of that /64. So this is summarizing kind of the first 64 for the network prefix, and then I have another 64 for my interface identifier. And so that's the minimum I'm always going to need. I have to have that to actually function. Again, there's always only one link local on each of my various interfaces. Remember, my default gateway also has one. The router has that. Normally it's : : 1, but it doesn't have to be at all. As we saw in Azure, it isn't. Okay, so that's interesting from a link local. But obviously I have an IP, I have a full address. If we looked again at our virtual machine, well, if we actually look at one that's real, but even this one, it has a full address. Like, how does it get the rest of the interface identifier if there's no configuration? If I look at my Azure VM, well, it actually looks a lot neater. My Azure VM, well, the link local address, yes, this randomized thing, but my regular IPv6 address, well, it has this actually, you can see the first 4 hextets, i.e. the network prefix, but the actual interface identifier is just 0:0:0:4. Why is that so neat? So there's actually different ways we get the interface ID. Remember, we have 64 bits. Huge, ridiculously huge number, which actually opens us up to some interesting ways we can behave and consider the laws of probability. So I have to generate this interface ID. So the first way is using something called EUI 64. So EUI 64 is this extended unique identifier, and it's basing it on the MAC address of the machine. Now remember, a MAC address is 48 bits. We see it as 2 hexadecimal characters, dash 2 hexadecimal characters, etc. So let's say mine is B4 dash 2E dash, trying to find my thing, 99 dash 36 dash 25 dash 36. That's my MAC address. That's the MAC address of my, let's say, my Ethernet card. So what it does, it takes that, remember that's the layer 2 that's used for the data link, and it splits it in half. Remember, I need to get to 64 bits. My interface identifier is 64 bits. I only have 48 bits, so I'm short 16. So it takes this and splits it in 2 halves. And then it sends it over here and adds FFEFE in the middle. So now what I get is, okay, B42E colon 99FF colon FE 36 colon 2536. So it's generated an interface identifier based on my MAC address by putting this FFE in the middle. Now it does one more thing. It flips the 7th bit. So the 7th bit would be in that 4 character. Because remember, if we think we're going from the left, essentially, it's saying that, so the first B was the first 4 bits, and so then that 4, if we expanded that out for a second, would be 0, 1, 0, 0, is how you get the value 4. So and then the B, that's number 11, which would be 8, 2, so it would be there, 8, 2, 1. So that's the B, so that's 11. So it's saying flip the 7th bit. So 1, 2, 3, 4, 5, 6, 7. So it's saying flip this one to then become 0, 1, 1, 0. Well, that's 6. So then that makes the address B6 2E 99FF FE36 2536. Now you might be wondering, why on earth is it bothering to flip the 7th bit? It's really for pleasantness when you're manually creating addresses. Because that 7th bit in the MAC address actually specifies, hey, is this a universal or local definition? Or is it universally kind of generated, or is it saying I'm locally setting? So universal is, hey, I'm basing it on some hardware token. Well, if I'm manually creating these IP addresses, I'm not basing it on some physical hardware token, which means the 7th bit should have a value of 1. That would be the idea. So if I was following the standard practices, if I was extrapolating all that out, well then this bit here, this 7th one, this is kind of, is it universal or local? So if I was manually doing it, well, I should set it to 1. But that would mean my address would be kind of 0200. So when I'm writing that out, that's really kind of a miserable thing for me to do as a human being, to have to be writing out 0200 colon everything else. So by saying flip the 7th bit, well, if I flip it, if it was 1, now becomes 0, I can just write 0. That's why they flip it. There's nothing more amazing than that. It's a convenience thing, because if I'm manually doing it, I would not want to have to do 0200. I can just do 0 colon. But the whole point of this is how it can generate the interface ID. It takes the MAC address puts FFFE in the middle of it, flips that 7th bit, and there we have our address. So we can always tell, it's kind of a magic thing here, if we see FFFE in the middle of the interface identifier, it means it's using EUI64, i.e. it's based on the MAC address. So that works, but there are some things people don't like about that. Because what does this mean? It means it's deterministic. No matter what network I'm on, if my interface identifier is based on my MAC address, no matter where I am, I'm essentially trackable. Any network I connect to, I will have a predictable interface identifier. So if wanted, I could track every network I ever connect to, because this will always be the same value. Also, because this now becomes a bit more predictable, if someone's trying to scan my network, I think there are different ways of looking at this, but realistically, if someone was trying to scan a network to find machines, if there's 64 bits of possible address space, that's very, very hard to scan. But if this is now based on the MAC address, which has, again, predictable values, it massively reduces that address space I would have to scan. Also, if I did then know the IP address, I can work out what the MAC address is, I can work out what the hardware vendor is, maybe I can do some hardware-specific type of attack. And so, that's one option. The other option is it's random. It completely randomizes it. And there are different algorithms that recommend how you can actually randomize it. So let's look at two different machines to see this. So we already saw this VM over here. So this one, if I look at this machine, if this is the interface ID, do I have FFFE in the middle? I do not. So I know this was randomly generated. It also has no correlation to my MAC address up there. And pretty much all modern operating systems use the randomize option. Let's compare that. It's funny, I actually installed this morning to my good old XP virtual machine. And I've forgotten how miserable it is to install Windows XP. But if we look at my Windows XP machine, let's look. And I could have done this on my Windows 11 or Windows 10. You can turn off the randomization, but it would be more fun to show you in IPv6. So let's look for a second. I have all these different IP addresses, but let's look for a second at my link local. What do you see in the middle of my link local? Well, you see FFFE. That means it's basing it on my MAC address, which I can actually see, because if I look at my MAC address at the top, it's 00. Okay, so you have to flip the 7th bit, so 0 would become 2. It's omitted the preceding 0, so I have 2. Then it's 155D, 155D, and then 564D03. Oh yeah, 564D03. So I can see exactly that. And it uses it also for other types of address up here. Oh, there's another one. It's using that same MAC address. And there's one that isn't. And there's another one up here that is based on my MAC address. And then another one that isn't. There's a whole selection of interesting things going on. Also, if you look, this is kind of fun to this, look at the default gateway for a second. My default gateway, remember that FE80 always uses the link local for my default gateway. Well, the link local is actually FFE. So the default gateway has actually based its interface identifier on its MAC address. So we can tell that's how it's actually working that out on its actual MAC address. So a little bit of fun. Again, the XP was, I thought it would just make it a bit more interesting. But we can see both of those options. EUI64, we're basing it on the MAC address. And we can always tell it's going to have FFFE. And go and do an ipconfig/all, or whatever OS you're using right now, and go and see. Look at your link local and see what it's using. But you can tell, is it using the MAC address or not? And also you'll see, well, the bits of it actually match the MAC address, apart from maybe it's got add2 added to the value of that second character. Or maybe if it's flipped. If it's based on the MAC, it's going to be added to, because it's flipping universal local. It will be adding 2 to it. So that's how we get the interface ID. That's what we're actually doing. So if we're using the random, it's just randomly generated. There's a whole bunch of different algorithms. The RFCs have recommendations on how to generate those things. It could be based on using that EUI64, then combining with the dates and digests and other things, tap your head, rub your belly, whatever. But there is a recommended approach laid out in the documents. Now you might say, wait a minute, if I'm randomly generating it, well, I might conflict with someone else. Well, firstly, if it's based on the MAC address, the MAC addresses are governed, so it really shouldn't conflict anyway. Randomly, ooh, it might conflict. Really? A /64 is, I think it's 18 quintillion possible addresses. If I conflict with someone else, I'm going to go and buy a lottery ticket because something clearly is happening there. So it's almost guaranteed to be unique just from the sheer law of probability. Now, there is actually something else that goes on as well. You ask Dad, duplicate address detection. So it does actually go out quickly and say, hey, does anyone have this? So it does triple check. But just because of the size of that address space, a /64, if I'm randomly generating it, the chance of anyone getting the same is minuscule. There was also something called a site local address. That's basically dead, so we're not even going to talk about that. But this link local, while key to the functionality, only works on my local subnet. What about when I want to talk to things on other segments? What about if I actually want to go and talk to the internet using IPv6? So next thing we then get into is there's different types of other IPv6 address we can use. And there's different ways we get configuration. So if we think about this IPv6 for a second, before I start talking about the next type of address, let's think about the actual components that at minimum are existing. Well, what we have to have is there's a router. For us to do any of the other types of configuration, I have to have an IPv6 enabled router. And then I have my client. That router, remember, I'm going to draw it as FE80 ::1. It doesn't have to be. It's fairly common to that, like we do .1 for the default gateways a lot of the time. We don't have to, as we've seen other networks don't do that. But it is always the default gateway. Even if I have other types of address, it is always the link local address of the router is the default gateway. And I always learn my default gateway from what we're about to talk about. It always comes from a router advertisement. So routers periodically, and it varies by the brand, but periodically they send out a router advertisement. Hey, here I am. With IPv6, there are multicast types of address. So what's actually happening, it sends out to all ICMPv6, it's ICMPv6 message to all IPv6 enabled devices. So this is actually a special multicast address FF021. There is no such thing as a broadcast in IPv6. But we have multicast that says go to everything that is IPv6 from my local address. So I'm sending out this router advertisement. Now what I can send out as part of that advertisement is, hey, a prefix that I want you to use for other types of address that actually could be used on the rest of the network, or maybe even out to the internet, and a prefix length. i.e. 64, basically guaranteed what it's going to be sending out. And then it also sends some flags. Now, this goes out every couple of minutes. Be advised. The client, remember, has an IPv6 link local, always. It always has that link local that it generates. If it starts up, rather than having to wait a couple of minutes, it can send out a router, and it will send out solicitation. i.e., hey, give me some info. At which point the router would send out the router advertisement and say, okay, here's the information you actually need. So it's going to send out the prefix and prefix length. It's coming from it, which will be the default gateway no matter what else happens. And then it sends these flags. And there's 3 flags. There's an A flag, an O flag, and an M flag. And these do different things. So I can think about A is address, auto configure. i.e. go and work out your interface ID. I'm telling you the prefix and the prefix length. So I'm telling you the first chunk. Remember, in the IPv6 world, I'm telling you the prefix ID, but the interface ID, you work out. I'm not going to tell you what to use. Go and work that out yourself. Which we've kind of seen already. Okay, well, we know we can use EUI64 or we can use random. So we know how to do that already. There's also an O flag. So this could be other configuration. i.e., hey, go and talk to some other service for a bit of additional information. Maybe like the DNS and the domain information. So what can also be on this network, I can think about, well, I have like a DHCP v6. So that can also be on the network. And then there's an M flag for managed configuration. And it's through these flags I can configure different combinations of things that the client will actually do. So let's draw these out for a second into how we can see all of this actually fitting together. So let's go different color. So I can think about the A flag, the O flag, and the M flag. So if I tell it to do address auto configuration, but no other configuration and no managed configuration, what we're telling it in this case is kind of our option 1. We're doing something called SLAAC. So SLAAC is stateless address auto configuration. In the router advertisement, I'm telling you the prefix, I'm telling you the prefix length. You can work out your own interface ID. And optionally, we can also send things like the DNS servers, and we can send the domain. So with this, I can actually optionally send things like DNS settings, domain configuration as part of that. So in option 1, there is no DHCP service at all. So this is no DHCP at all used as part of that conversation. The next option is, hey, yeah, auto address configuration, but yeah, there's some other config, but you're not managed. What this is going to do, this is SLAAC plus stateless DHCP. What does that mean? That's kind of odd. Okay. Well, remember there is that other information. So in this option 2, what it will do is it's going to generate its own address from the prefix, but instead of this sending it DNS domain information, there might be other things as well. Well, this is where it's going to get its DNS and domain information from. So that's that option 2. So I'm going to go and get that from the DHCP server. Is not having address pools. It's not tracking IP addresses. It's literally just got some additional bits of config that my machines can go and get information from. Option 3, let's use a different slight different color on this one. Option 3 is stateful, DHCP. Now here, I want this, it's got to be 1. I want this to be 0. Technically, I could put 1. If I put 1, what it will do is it will still generate an automatic address, and it's going to get one from DHCP, which I probably don't want. So I want that to be 0, and that's going to be 0. So in this scenario here, the client will essentially ignore everything about the prefix and the prefix length. The default gateway is still coming from here, always, no matter what. If this is scenarios 1, 2, or 3, default gateway is always coming from that route or advertisement. But now in option 3, it's actually sending it, the DNS information, the domain information, and the address. It has a pool of addresses, and it's giving them out. So now it's stateful because it's tracking it. It's giving out that specific address. And that's really the whole point of how that functions. And that's why we kind of saw what we saw when we looked at Azure. So remember, if I looked at my regular machines again, this was my XP machine. So this is running locally in my environment. You can see I have a set of different addresses over here. And we're going to go into why they're different in a second. But my interface identifiers, we noticed I had 2. And that's obviously because what it's doing is, it's getting one from a DHCP service, and it's getting one from an auto address configuration. But they're really long because they're just randomly being generated or they're being built off of the long MAC address. Compared to if I look at my XP virtual machine, well, that's using DHCP essentially behind the scenes. So if I look at my address for my IPv6 over here, remember this first 4 hextets, that's all the network prefix. My interface address, my interface identifier is 0:0:0:4, i.e. that was not randomly generated. Something gave me that. Something had a pool of addresses and gave me that address. So that's how we can kind of see actually, that makes a lot of sense then. So I can kind of tell, obviously in Azure, and here's a big one, in Azure, obviously it is stateful DHCP-v6. It is not randomly generating stuff. It is getting addresses from some authority, which is the software-defined virtual network stack. Now, in all of the circumstances where I am using address auto-configure, we said that SLAAC, that stateless address auto-configuration. We have seen that already. Anytime we are doing this, we're doing this. We're doing this EUI thing, or we're doing that random. So that is SLAAC. That's how it generates the interface identifier, and it adds that duplicate address detection. Just to triple check, even though it should be unique, it's a tiny, tiny chance that someone else is using that because of the size of the address space. But just in case, we'll just do a quick kind of solicitation out there. Hey, anyone got this already? No? Great, this is me. But again, if you did get a duplicate, there's something really kind of weird going on. So we've seen how that works. Remember, if we're using managed config, it's given out from a pool. We don't have to do that. We're not generating the interface ID. It's coming from a managed set of configuration. So that's how we get those additional configurations. So the router actually tells us how we should go about getting our addresses. It can tell us the prefixes that it wants, and it could be multiple. It could give out multiple prefixes and multiple prefix lengths for the interfaces. And then I'll go and follow my directions for whatever I should do to actually get those actual addresses. And that's a key thing. We can have multiple IP addresses for each interface. And it was kind of a hack to do that on IPv4. It's very much a designed by feature of IPv6. This leads to some different types of IP address. So if we think back to our network, remember, on our network, okay, link local is great to talking to my local subnet, but what about if I want to talk to everything on my internal network? I want this entire scope. And there's two options. And we're probably going to have both. Maybe I shouldn't have said that. We may just have one of them. It really does depend. And there's even a little bit of, I think, of a debate going on about what is the right answer. So take this as it does depend in this particular scenario on your company. But one option is there's kind of a scope that would span my entire network, unique local address, ULA. And that unique local address is always going to be FD/8. So it's defining that. It's actually a /7 and it's FC. But right now the 8th bit is mandated to be 1, i.e. it's locally generated, which gives you FD. There is no universal management of this unique local address space today. So the 8th bit will always be 1. So if it's FC is the first 7 bits and the 8th bit is always 1, well, C plus 1 is D. So it's always going to be something FD. And just like the RFC 19, the scope of that stops and will not route past kind of that edge. It will not route over the internet. But it will route over all your kind of internal routers. Now, I want to be super, super important clear. It's similar to RFC 1918 in that it's designed for kind of an internal network space, in that it doesn't route over the internet. But remember, RFC 19 was really built around the idea of going to work with NAT. It doesn't mean I don't necessarily want to NAT this. This is not saying I want to NAT at the edge. Generally, we don't need to NAT IPv6 in most circumstances. It's useful that I can get an address space that is independent of maybe my internet service provider. That's kind of a key point. I want this, and I'm going to talk about this because maybe I need some address space that will be consistent between different network segments that can't be changed by my carrier. And I just want to have that consistency that I can manage. So this is the next type of IP address I could have. Oh, this is a big picture. So if we had that idea of that linked local address, and remember this interface ID logic applies to all of these types of addressing. It's always going to use it with linked local because there is no stateful option. There's no DHCP server for linked local. But when I use that auto address configuration, this same logic will be used for all of these other types of IP address I'm going to talk about as well. So I always have one and only one linked local per interface. So the next thing I can have is this unique local address, that ULA. Now, this is actually defined as that FC/7. So remember, we're always going to break down that prefix into 64 bits. So if I think about the prefix as a /64, it gets broken up into a number of different components. So the first 7 bits is FC. The next bit is this kind of universal or local one. Today is always going to be 1, which is why it's always going to be FD when you add that for the first 2 characters. The next 40 bits, random. And that's an important word. When they use the word random in these requests for comment, these RFC documents, it really means random. There's a whole set of algorithms that it recommends to guarantee the randomness of that value. So it is this randomly generated global ID. Now, although this is not routable on the internet, it still is going to be universally unique, most likely, because it's 40 bits being randomly generated. So the chance of it matching someone else out there is infinitesimally small. So it's going to be this random number. Then that's 48 bits. The next 16 is used for subnet. And that's kind of a key point now. So what it's giving me is the first 48. So remember, it's 8 bits. So there's a hextet, 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 hextet. So the first 3 hextets are basically this value for the network. And then I have 16 bits for the subnets I need. So 16 bits gets me like 65,536 subnets. So I can have a massive number of subnets. And then, of course, I have the interface ID, which is the other 64 bits, which randomly generate using SLAAC, or if it's DHCP, it's going to tell us what that actually is. Now, a nice point about these is they are completely separate from any kind of provider I might have. So I'm not relying on my service provider to allocate me these values. It is just something that I generate, and there are websites you can go to that will randomly generate these for you. There are some sites that try and track what these are, but it's not mandated at all. The benefit, you might say, why do we bother with this random value? One of the pain points today is with regular RFC 1918. I pick one of these, and I'm quite happy. Then I buy another company. We want to connect the networks together. We both use the same. We can't connect. By having this randomness in that unique local address, if I do need to connect to another network in the future that's going to become part of my internal network, there's no chance we've used the same addressing. So I'm going to be able to connect them. And once again, because I am defining this, if I have multiple different physical locations, I can still use the same consistent prefix that I've generated across everything I have. I'm not going to have these disjointed address spaces that I may get if I had some carrier giving it to me that is part of their address space. So it gives me the ability to really have control and guarantee it's not going to change. Even if I don't have internet connectivity, if this was an isolated network, a secure network, a lab network, which again, there were some arguments back and forth about if you should really use ULA or not. But I would definitely use it in those circumstances. If I'm disconnected from the internet, I have to use it. But again, a lot of companies will use it even if they do have connectivity because, hey, I have multiple locations and I don't have some other global address space that I can use. And we see exactly this. So we see in our environments, if I look at my demo VM, you can see my IP address for my IPv6 is, we go and look over here, FD. That means this is from the unique local address space. And then what we have is the next 40 bits is all random. That's all just randomly generated. And then we can see, well, that's the subnet. Oh, so, okay, this is my first subnet. So it's this 3 hextets for that prefix that makes up the global portion. Then my subnet, and the next 4 hex text is the actual interface ID. In my case, 0:0:0:4, because again, this is being given out by DHCP, so it's not that random kind of number. But that's one of the options. So it's like RFC 1918 in that it won't route over the internet, but it's not designed that, oh, this will be my only address, and so now I have to NAT at the edge. We really shouldn't have to NAT, for the most part, IPv6 because of the size of the actual address space. Okay, so what is the global address space then? If that's what you're saying, you shouldn't have that, what is the next one? So the next address space we have is, I'm going to pick a slightly different color. We have this idea, and notice I'm drawing it differently. We have this idea of this global unique address. Because remember, IPv4, there weren't many of them. There's no way I could give real addresses to everyone in my company. So I only had on their edge router a real address. Everyone else had something from the RFC 19. Not so with IPv6. There's a big enough address space that my machines can also have one of these. So it's going to also have this. And remember, I can have multiple. So when I think about the addressing, we also can have this globally unique address. Do not confuse the fact I have a globally unique address, meaning the same thing as it's addressable from the internet. NAT was not security. Security is the firewall, the stateful inspection. So even if I might have a valid IPv6 address, I'm still having firewalls on my edge to protect who can come in and who can get to what services, what can I get outbound. NAT was not a security mechanism. That's really important to understand, because you might go, oh, this is horrible. All my machines now have globally unique addresses. You have the edge where you protect. You have defense in depth, and I still have protection at each layer. I have protection on my firewalls, all these other components. That's the protection part of this story. So we have this globally unique address as well. And I'm trying to find, okay. So we had the unique local address. The unique local address, remember, was optional. So optionally, I can have one or more. I can have multiple of those. Then, also, I can have my global unique address. So that is my GUA. The global unique address is essentially 2000/3. So they are only mandating the first 3 bits. So it could be 2 for that first character, or it could be 3, because the 4th bit could be a 1, which would make that value 3. So if I think about now that address space, so firstly, remember, this is allocated. I am not making this value up randomly. This is a centrally controlled and centrally registered address space. So that means a few things. When we draw out this idea, yes, one option is I get it from kind of the IANA, but most likely I'm not. Most likely is, yes, it's managed by this greater authority, but for me as a company or me at home, it's actually probably my ISP is allocating from their range. So they have some big chunk, a higher aggregation of these values. They probably don't have a /48. They might have some other portion of that address space. Then they can give out a portion of that, or they might just give me out a subnet, essentially. It depends on if I'm just a home user or what I am. So I'm not getting it directly unless I'm a really big company and that's one of the challenges. I'm getting it from my service provider. So where that becomes an issue, if I had different offices in different locations, well, my service provider is giving me this globally unique address space. So one office may have one prefix, another office has another prefix, another office another prefix. That's where it gets kind of ugly from managing my routing internally. And it can be done, but it just gets kind of ugly. That's why it might be nice to also have the unique local address space that will be consistent no matter how many offices I have. Also, that provider, what if I change providers? That whole address space has changed. What about if they just change it for some reason? Well, it's all changed. Now, it's designed to be dynamically used and calculated, so it should be fine. But it gives me that isolation from the address space of the service provider. And again, there's a whole set of debates. What's right or wrong? Some will say you should not have to use ULA, you can just use GUA. Others will say, no, that works for a home user. That works for a huge company that actually goes to the INA and gets their own /48. For everyone else in between, this doesn't work, so I'm going to get these different address spaces. I want to use the ULA as well. But the whole point is we have this globally unique address. Once more, I can have one or more, and they're optional. I don't have to, I could just have a ULA, and then I would have to do like NATing at the edge router to actually talk to things on the internet. Or maybe I'm only using it internally. Or I can have GUA. And no, I might have a GUA and still do NAT. Well, not even NAT. I don't have to maybe do the port translations to the address space. I might just be doing MPT. There are things I can do. But if we break down this address space, so this is allocated or our kind of, essentially our service provider. And then what we're going to have this time as part of that prefix, we have the same idea. Again, it's always the kind of that /64. The way they're allocating it now is the first 3 bits is 0, 0, 1. So 2, because it's a 0. But the next 45 bits, well, that's the global routing prefix. That's assigned to us. So again, technically, if the first bit was 1, that would become a 4. Sorry, that would become a 3, because obviously 001 is 2. So it's generally going to start with 2, but technically it could be it could be 3 if the next digit was 1. So we get this, and then once again, the next 16 bits I use for subnets to divide up that space. And then once again, my interface identifier is 64 bits. SLAAC, assigned, whatever that might be. And so for both of these, that globally unique address and the unique local address, you see the same pattern. If you think about the blocks for the network prefix, it really is breaking it down into the idea of 3 for kind of the main, the network prefix, 1 for the subnet, and then 4 for the interface ID. So it's kind of this 3-1-4 rule, and that's consistent across both of them. So globally unique and for the unique local address. The first 3 hextets are used for the network identifier. The next 1 is used for the subnet identifier. And the next 4 are used for the interface address, which is why you saw my VM in Azure, that 4th block was just the value 1, because I configure that. So once again, a value of this might look like, okay, 2008. D, I'm missing off the trailing 0, DB8, then maybe it's ACE, yeah, ACE, and then my subnet. So maybe my subnet is subnet number 3, and then my interface address is 10. Because, hey, I'm using DHCP, so it's not some huge value. So it's 0:0:0:10. I've omitted all the sequential blocks of zeros, and I've removed all the trailing zeros from the subnet, and here as well. So that's what that might look like for that global address. And if you think about that, that's really a tiny amount of the overall address space. So they're not using a huge amount. And you may wonder, this is actually reserved for documentation. So 2008 DB8 is reserved to use in documentation, which is why I feel okay writing that down. It's like 555 in movies. No one is actually using that. And if you go and look at your house, you might have actually a subnet assigned to you. Like if I look at my AT&T gigabit, they've given me a /64. So they've assigned me a subnet from a space. So they gave me a specific subnet. So I have 64 bits available for my house, so every device. So I could have 18 quintillion devices in my house. I don't. I hope I never do. But I could. Because it's that big of address space, these carriers can kind of give that out now, because there's just such a large amount actually available for this. Remember, it is not an either or. This is not like IPv4 where we have an IP address. What we absolutely would expect to see is if I am using ULA, I probably do have a global unique address as well if I'm connected to the internet. These are used first, so this will be preferential on my internal network. And then if I'm trying to get to something externally, hey, I might go and use the global unique address to actually get to things externally. And it's still the edge has firewalls and stateful inspection to make sure I'm not talking or exposing to things I really shouldn't do. So that's really some of those are the key types of address. Now there are others. There are multicast. We talked about the FF02::1 to talk to all IPv6. There's a FF02::2 to talk to all IPv6 routers. But again, there's no broadcast. There's Anycast, where it's just another address, but multiple devices can use the same one, and the first one to see it can kind of respond, gives me kind of that resilient capability. But the key point for IPv6 is, hey, yeah, I very commonly will see multiple addresses. Don't think of link local as just some thing. It's a core part of how it works. I'm always going to use the link local of my local router as the gateway. And then in addition, I'll probably, I will, in an IPv6 enabled network, I'll have one or more unique local and or one or more unique global unique addresses. The whole point is these global unique actually will route over the internet, whereas unique local addresses will stop. They will not get routed over the internet. They'll get dropped. They're not going to go anywhere. So that's it. Obviously, there's a lot of content there, but it's really not that hideous. It's nice to understand. It's kind of cool to understand how they're using it, how they generate these things, how the different parts come into play. So let's actually finish with, okay, great. What about Azure? So now we're switching to the Azure part of this. And this is super quick now, because once you understand IPv6, you quickly understand there's nothing actually particularly special about thinking of this in Azure. So obviously our core building block of networking is going to be a virtual network. Now a virtual network is always one or more IPv4 CIDR ranges. So it's a set of IPv4 ranges. And remember, we always break up that virtual network into subnets. So I can create multiple subnets. And a subnet is always a particular IPv4 portion of that IP space. So it's a certain portion of that space. So what we can now optionally do is, well, I can add, let's do this, an IPv6 CIDR range. I wrote 4 instead of R. Oh. So I can optionally, I can do it when at network creation. I can add it to an existing. There are some restrictions to add to existing. If I have service endpoints, they do not support IPv6 today. It will not let me add IPv6 to the virtual network. But assuming not, I can add it to an existing. And then I can optionally enable an IPv6 CIDR range to a subnet. It will always be a /64 in Azure. Again, it's kind of the standard anyway, but I have to do /64s for subnets. This ensures compatibility with many types of router and routing infrastructure. So I have no choice. And just like regular subnets in Azure, I'll always lose 5 IP addresses. You always lose 5 for IPv4. You always lose 5 for IPv6 as well. The whole gateway DNS, all 0 or 1, you lose those. So you'll always lose 5 IP addresses, which is why, if you think about it, my Azure VM, this was the only VM in the network. Well, why do you think I have an IPv6 address of 4? Well, it's because 4 is the first usable address in the subnet I created. So that's why I have that. If we actually go and look at my virtual network, I think it's that one. Yeah, so you can see I gave it an IPv6 range. Now notice I did a /56. I did not do a /64. The reason for that is, remember that the network itself would have been a /48 because 16 bits are saved for the subnet mask. But what I did is kind of split that, because maybe I've got multiple virtual networks. So I want to be able to take that overall /48 network I generated from that random, because I'm using that unique local address space. I want to be able to have different virtual networks and use a portion of that space. So I have that consistent space across all of them. Maybe some of it I'm using on-prem, which is why I talked about the client will always see a /64, but in terms of how I divide up that network, well, I'm using a portion of my /48. So I could use another portion on another virtual network. So that's why I added a /56. And then for my subnets, we can see I added an IPv6 address space. Now that is a 64. And we can see, yeah, the subnet, remember it's that 4th hextet, is just 1. And then it's telling us, yeah, okay, that's how it's then given out. And it's just saying more than 10,000 mostly IPv6 address spaces. It's not giving us an exact number. But that's now lit up for the actual virtual network. Now a key point here, this is where it can get a little bit confusing. Azure is still following, in a lot of ways, the IPv4 model. So this IPv6 CIDR range here, technically, you could use a globally unique address space. Or I can use a unique local address. You are generally going to use unique local address. Because even if I use the globally unique address space, and maybe I will because I already have it, and it's, again, consistency, it will not be used to talk to the internet. This space is private space. It is private IP space. Doesn't matter if it's a GUA, that globally unique address space, it will not be used to talk to the internet. It does not work that way in Azure. So most of the time in Azure, I'm going to use kind of this unique local address space. Because even if I use a GUA, it is not being used to talk to the internet. It will not work that way. So we add it to the VNet, we add it to the subnet. Because it's private IP space, no matter what range I use, we're probably going to use unique local address space. But we could, if you wanted to, use the GUA, but we're only using one. And then if we think about resources, so inside here, I have a virtual machine. Remember that virtual machine has a NIC. And what we add to that NIC is essentially we have IP configs. Now it always has an IPv4, and that has to be the primary. But then we can add an IPv6. It's only one per network card I can have, but I can then go and add an IPv6 config to it, but it will always be secondary. Azure is dual stack. I must be IPv4. I can add IPv6, but I must have IPv4. I cannot turn off IPv4. I can, in routing, only listen on the IPv6, but the resources themselves have to have an IPv4 address. So if I now go and look, what I've actually now got is if I look at my virtual machine, I look at its NIC, if we look at the IP configurations, we can see I added an ipconfig 6. Notice it has to be secondary. And we can see it got an IP address. It's dynamic. It took the first one available from the subnet. So it's 4 because we lose the first 0, 1, 2, 3 and last one as part of it. So 4 was the first usable. So I now have an actual IPv6 address. And that's it. I've now added it. So this is now lit up for IPv6. Now, in terms of the actual communication, if I had other subnets, other virtual networks, sorry, and they had IPv6, and I peer them, local or global, that works. If I had on-premises locations and I had kind of my gateway running in here, my express route gateway, and I configured express route private peering, and I do the IPv6 configuration, IPv6 works there as well. So I can have IPv6 going from on-prem to my virtual network. I can have it going across peered networks as well. That's just going to work. What about talking out to the internet then and offering services on IPv6? With IPv6, it's different from IPv4. With IPv4, there was this default outbound IPv4 address. There was this pseudo IPv4. So even if I didn't have a public address, I wasn't behind a load balancer, I could speak IPv6. That is not the case. Sorry, I can speak IPv4. That is not the case with IPv6. If I do not have an IPv6 public address or behind a load balancer that has an IPv6 address, I do not talk IPv6. We can see this. So if I notice on this network configuration, there is no public IPv6 address. It's blank. So if I go to this virtual machine and I go to what is my IP, public IPv6 address is not yet detected. You do not have one because there is no default IPv6 lit up for me. Now, if I go to my config and I associate a public IPv6 address now to this virtual machine, so let's go and make that update. It's going to take a little minute because I'm obviously trying to demo, so it's going to take its time today. So that's saved. Now this may take a second, but let's go and see what happens. If I refresh, not yet. And it worked. So now I do have an IPv6. That's that public IP, and it's coming from Azure's range of addresses. Well, now I have an IPv6 address. The same thing would work if I actually went and put it behind a load balancer. So I'm going to disassociate that again, just so that goes away. So in terms of thinking about the public ID, I have to create a public IPv6 address. So I would create a public IPv6 address. Or I could use a prefix, Prefix, remember, is a contiguous set of addresses. So either I could associate it to the IPv6 config, or the preferred approach normally, hey, I have a load balancer, and on the front end, I would use that, and then these become back-end set members. Either way, I would then go and use that to actually go and talk. Now, talking of load balancers, yes. So load balancers support IPv6. It is not doing any kind of NAT 6-4 or any translation. So the back-end set members must be dual stack. If I'm using IPv6 on the front end of my load balancer, everything on the back end must be dual stack. It must talk IPv6 as well. Now this does mean when I do talk to the internet, it is going via this public IP address. It is actually SLAACing, which is not super common. We wouldn't normally advocate that in IPv6 world these days, but that's the way this is working today in Azure because it's following that IPv4 model in terms of how it's kind of breaking up that IP space. Today, NAT Gateway does not support IPv6. It can live in a network with IPv6, but it does not actually provide IPv6 outbound. Things like network security groups, UDRs, so I can do user-defined routes. They all work with IPv6. Talked about the load balancer configurations. DNS, so we have Azure DNS. Now remember, Azure DNS has two types. There's public and there's private. So the IPv6 equivalent of a host record, an A record, is an AAAA. So an A could be 32 bits, so AAAA is 128 bits. I'm sure maybe that's the reason, maybe not. I don't know. But they both support that. Yes, IPv6. But one of the things you can normally do with a private Azure DNS zone is you can, when you link it to a virtual network, so we actually go and we put in this kind of link, we set this up. So one of them is for resolution, but the other thing we can do is registration. That will not work for IPv6. It will not register Quad A records for IPv6 in my virtual network. It does not do that. So that's kind of an important thing to understand. Now, beyond just the very basic services, it varies. Things like Azure Kubernetes Service today has support for dual stack IPv6 if I'm using KubeNet. So KubeNet is where the pods run in their own separate IP space from that of the virtual network. But it does not work if I'm using CNI, i.e. the pods get real IP addresses bases from the virtual network. Azure Front Door does work with IPv6. Other services, it really just kind of varies. So you're going to need to go and look at the exact service to understand does it or does it not work with IPv6 today. I think obviously this is a big push. There's a lot of industries that are mandating IPv6 over the next couple of years. But from a structure perspective, there's nothing groundbreaking about it. It's really, do the services support it or not? But the important thing is to understand IPv6. So hopefully my goal for this was to explain IPv6. And once you understand what it is, it's a different type of address. It's actually simpler in terms of the subnets. It's pretty always going to be a 64. And there's pretty much always now that full hextet for unique, local, and global unique is always going to be used for the subnet. It makes a lot of sense. Azure is always going to do that stateful mode. It's always been allocated from the address space of the subnet the resources in. But if you're playing around looking locally, hey, that link local, remember, for older OSs, if you see FFFE in the middle, it's using the MAC address. Most of them will randomize because of the security and other implications and tracking of basing it on a predictable value. But that's it. I hope that was useful. I thought it was fascinating. I'm actually seriously thinking about doing an IPv6 masterclass as my next masterclass because I loved really investigating and playing around with this stuff. But go and look at your network at home, do an ipconfig/all and see what you can see. And maybe go and look at your gateway router from your ISP. what did they allocate to you? Do you see a /64 allocated to your environment? Go and have a look. As always, a huge amount of work goes into these, so I really would appreciate a like and a subscribe. But until next time, take care.